invited and featured in the IEEE ISAC Best Reading list. He has delivered 6 tutorials, over 15 keynote speeches, numerous invited talks and webinars, and co-organized over 10 international workshops, special issues, and summer schools. Additionally, he plays a leading role in shaping ISAC's global research agenda. He currently serves as the publication co-chair of the IEEE ComSoc ISAC ETI and EIC of the ISAC ETI newsletter, co-chair of the ISAC SIG within the IEEE Green Communications and Computing Technical Committee, and an elected member of the IEEE Signal Processing Society ISAC Working Group. Now, let's welcome Professor Zhang to give us the exciting talk.
Thank you very much, Professor Yang. Let me share my screen. Okay, can you see my screen?
Yes, okay.
All right, great. All right, it's my great pleasure to be invited to provide a second guest lecture on ISAC technology organized by Chess Park. People always ask, particularly the industry people, what are the actual killing applications of ISAC technologies? Today, I try to provide some examples, particularly in applying ISAC technology for environmental sensing, including rainfall, intensity, and water level sensing. The outline of this lecture is like this. First, I will provide some background introduction briefly, mainly on what is Perceptive Mobile Network and what is biostatic sensing and their roles in the environmental sensing. And then we will have a look at water level sensing techniques and then rainfall sensing. So in my last lecture, I already provided a detailed discussion introduction on the so-called Perceptive Mobile Network, where the ISAC technology is systematically applied in the mobile network. So to realize sensing, basically we can have 3 approaches. One is standalone base station based and using monostatic sensing. So the base station, for example, receive the signal of the reflected echo from its transmitted one for sensing, right? Another one is still standalone base station, but it's in a biostatic setup, which means the sensing signal is from the user terminals in mobile network. These user terminals are mobile phones, etc. And the third type is called network sensing, where multiple transmitters and or multiple receivers are involved. To do actual sensing, we can, for example, use the channel state information estimated from pilots. We can also use other signals, for example, the synchronization signals and as well as the random data payload. In addition to doing sensing at the base station side, certainly we can also do sensing at the mobile side, right, at the user side. So either uplink or downlink signals and their reflections can be used for sensing. Biostatic sensing means the sensing is realized between geographically separated transmitter and receivers, and the clock asynchronism is a critical issue to be solved so that biostatic sensing can be realized. The clock asynchronism means the underlying hardware clock are not locked between the transmitter and the receiver. As a result, there will be multiple offsets caused, for example, random phase offset, delay timing offset, and carrier frequency offset, as shown in the red symbols in this equation here. To resolve biostatic sensing, we have to either remove or estimate and compensate for these offset terms. And existing techniques can be classified into mainly 3 classes, so including offset cancellation, which try to cancel the offsets instead of estimate and compensate for them. And of course, on the opposite, we can try to estimate and compensate for the offsets. So this is a second class of technique. And there's a combination of these two as a hybrid approach. And under each category, there are also multiple subclasses of technique. One main technique exploits the fact that the clock offsets between multiple antennas and the single transmitter, they are the same, because quite often multiple receiving antennas, they are supported by the common clock, right? So this means the clock offsets across antennas, they are identical. So by exploiting this property, we can realize cancellation by, for example, simply multiply the signals between multiple antennas, or even do division. We can also extend the spatial domain processing to the delete domain. We have shown the details in the last lecture. So today we will mainly discuss how we can apply these biostatic sensing techniques to solve the water level and the rainfall sensing problem. Now let's start to look at the detailed sensing approaches. First, I would like to introduce a recent paper which provides a good overview for the topic of water level and rainfall sensing. The advantage of using 5G network as an environmental sensor is obvious, because it doesn't require the deployment of dedicated sensors, right? So this can save huge installation and maintenance cost. The mobile network-based sensor, it can also realize ubiquitous coverage and 24/7 in this continuous operation. When we conduct such a research, we generally use the following approach. For example, we first develop some sensing schemes, and then we validate these sensing schemes using simulations, right? And once these schemes are validated by simulation, now we can try to test their performance in real environment. So we will build platforms and test beds for both the data collection and the algorithm validation. To better understanding how the sensing performance are affected by different components of the algorithm, we can first, for example, do in-lab experiments under controlled conditions. Right? So this can allow us to separate, for example, many interference sources from the experiments in the lab environment. And then we will deploy the system in real field. While we try to collect data sets for both testing and validation, there are a lot of practical interference sources needed to be considered and try to suppressed. Actually, this would be the key research challenges in the environmental sensing. We also considered both using downlink and uplink signals for sensing. For the downlink sensing, we developed some software-defined radio-based system, while also we used the existing mobile phone for sensing. For uplink sensing, we mainly use the signals received at the base station from mobile phones for sensing. In this scenario, because the current base station doesn't provide, for example, channel state information, we cannot fully explore the potential of using channel state information. Rather, we can only use the statistical for power metrics of the received signal. We are going to discuss the details later. But even with such a simple statistical results, we can still realize some interesting sensing results. We have also tested various mobile systems, including the sub-6 gigahertz conventional, for example, frequency bands around 3 gigahertz for AOT and 5G systems. We also tested millimeter wave mobile networks. Here is a general architecture for doing the sensing. So for environmental sensing, we can adopt both model-based and data-based approach. We can also mix them, combine them, and adopt a hybrid approach. So this block diagram shows the typical data flow or processing flow. So first, we will capture mobile signals, either CSI or the statistics of the power matrix. And then we will try to apply the biostatic sensing technique here to extract feature signals. During this process, we will remove the offsets, various offsets due to clock asynchronism. We will also incorporate techniques for interference suppression, etc. We will discuss some detailed examples shortly. And once we extracted the feature signals, then we can apply machine learning techniques to either realize regulation or classification, right? Then we can output the sensing results. So this is a general processing flow. We have various equipment and devices in our lab. With the usage of them, we collected various data sets in real environment for both water level and rainfall sensing. For example, we have the 5G system emulator based on OpenAir, which can emulate a base station of 5G system. We also have the millimeter wave transceiver, some dedicated antenna arrays, a Wi-Fi sensing platform, and the in-lab swimming pool used for water level and rainfall emulation. And also a millimeter wave, so a massive MIMO testbed, mainly used to simulate the AOT system. Of course, when we apply the SDR system outdoor, we can directly capture the signals from base stations, and we can use customized software to decode the received signal. Particularly for AOT, we always extract the pilot signal and get the channel state information for sensing. These photos show the various experiments we conducted in the scenic area, including in my backyard. So you can see there are a lot of trees, etc., in the surrounding environment, right? Particularly when raining, these trees will swing a lot, and such a swing will cause significant interference to rainfall sensing. For water level sensing, there are also, for example, boats passing, pedestrians walking along the path, and even nearby vehicles will cause interference. So for real environmental sensing, there are so many interference sources, and we have to suppress their impact before we can conduct efficient, effective sensing. Okay, now let's first look at how we can do water level sensing. We have several papers available on arXiv. We actually have done this project for more than 2 to 3 years now, but our publication is lagged behind. It's mainly because we are submitting multiple patent applications, so the publication has been delayed. The underlying principle for water level sensing is relatively simple. For example, let's look at this setup. We have a base station seeing signals from mobile phone, and there will be some static paths between the mobile phone and the base station. There will also be at least one path reflected from the water and reach the base station. So in this scenario, when the water level varies, we will see the propagation path will change, right? There will be multiple changes. For example, the propagation delay will change, as well as the angle of arrival. But these two variations are very hard to detect because their variation is very small, right? I will show you one example shortly. so what we can actually detect? We can detect the phase variation caused by the propagation path length change, right? And such a change only if it's, for example, comparable to one wavelength, then we will see a completely cycle of phase variation, right? So signal phase is the feature or the variable that we can extract for water level sensing. Particularly, if we do not separate the two type of paths, the combined signal will show some periodic changes, right? For example, if the propagation path changes over one period, then we will see the combined signal's power will show the variation as shown in the black curve here, right? So this underlying principle is quite simple, and such a periodicity is proportional to the carrier frequency, or in other words, the period of the cycle, as shown here, is inversely proportional to the carrier frequency, because we know the phase is the product of the light of speed and the delay, right? The time delay, it's related to the distance variation, and so this means the higher the carrier frequency, the shorter the period, and vice versa. So for real environmental sensing, we needed to solve multiple practical challenges, although the underlying principle is quite simple. For example, how can we know which period the current estimate locates, right? So we have so many periods here. And for high frequency signals, the period is very small. So when we see the signal, for example, here, we don't know exactly what's the water level corresponding to, because each cycle looks very similar for different water levels. And this may not be a severe problem when the carrier frequency is low. For example, in this scenario with the 3 gigahertz carrier frequency, we only have slightly more than one period as shown here, right? But when the carrier frequency increases, or the variation range of the water level becomes large, we will always face the problem how to determine which cycle the current estimate is. Another issue is how can we know whether the water level is increasing or decreasing? Because when the water level reaches a certain value, the received signal, the power in particular, it will reach, for example, at the peak or the bottom of the valley. And next, when the water either increase or decrease, we will always see the same piece of curve. So we do not know whether the water is increasing or decreasing at the moment. Right, so this is another challenging issue. The third issue, and even probably the most challenging issue, is how to suppress various interferences, as we just mentioned. Another factor which we typically ignored is that in mobile networks, the power of both mobile phone and the base station, the transmission power, actually varies, right? It varies in a period of 24 hours. This is the fact that we observed from multiple measurements. So the power variation itself will be mixed with the variation caused by water level. So it's a critical issue to separate these two types of impacts. We developed two types of frameworks for water level sensing. One is mainly based on signal processing, and another one is primarily data-driven, based on deep learning networks. For the signal processing framework, we also developed two types of techniques. One can work for a receiver with a single antenna, and another one works with multiple receiving antennas. When we have multiple receiving antennas, we can incorporate a powerful beamforming technique, for example, to get to suppress the interference and enhance the signal, reflected signal from the water. We can also realize angle of arrival estimation. Such information actually is quite important for us to translate the estimated propagation path variation to the actual water level variation. All right, I will show you a simple equation for this conversion shortly. So this is the basic processing flow for the single antenna or multiple antenna based signal processing framework. So once we captured the channel state information, this is based on particular for experiment. This is based on the software defined radio and using downlink signals. So for the captured carrier frequency signal, we first apply biostatic sensing technique to remove the offsets, while at the same time, we try to suppress various interferences. And then we extract the water level feature, and then we do a translation from the estimated propagation to the actual water level. Right? Sometimes we also need some smoothing technique based on, for example, Kalman filter, etc., to smooth instantaneous estimates and get improved output. For this particular scheme, there's no training required. Right? We don't require data calibration, etc., for get a real-time estimate. Once the system is deployed, we can get the estimate instantaneously. So it's very robust in terms of deployment or the locations. Let's first look at the single antenna-based signal processing framework. I should highlight that this is not the only solution. All right? We just show one possibility. Okay, once we get the channel state information, we exploit the CSI power to remove the offsets. All right. So in other words, now we just use the power of the received signal. It's of course we can also have other approaches to remove the offsets. For example, as I mentioned in the last lecture, even for single antenna, instead of doing cross antenna cross-relation in the spatial domain, we can also do this in the subcarrier level in the frequency domain. But here we just use the example of power of the received signal for offset removal. And then what we do a Doppler transform across the snapshots. So we have multiple measurements across the temporal domain, and we call them snapshots. This will enable us to generate Doppler frequency estimates. But the issue is because we only use the power, as I just mentioned, it's hard to know whether the water level is increasing or decreasing. In other words, the resulted Doppler frequency, whether the positive or the negative component is the correct one. Because when we use the CSI power, this is real signals, right? After doing DFT, we will get a complicated outputs with the symmetric image components. So that's why we have both positive and negative component here. At the same time, we will use techniques to suppress interference. In particular, here we use the MVDR technique, minimum variance distortionless estimator for the range estimation and interference suppression. Then we can get a 2D Doppler delay estimate or heat map. So note that in real system, we will not have negative delay. So exploiting this property, we can remove the image component and return the correct estimate. Right? Of course, there's some special processing here so that the condition I just mentioned can become true. Exploiting this technique, we can remove the image component and get a relatively clear output. Shown here are two examples. One is based on 28 gigahertz millimeter wave, and one is for 3.1 gigahertz. So as you can see, the resolution here is quite different, right? So for example, for this one, the spot almost covers 4-meter range, while for millimeter wave, it's only 1 meter in this particular example. And we also have non-zero Doppler estimate for the output. So these Doppler values, they corresponding to the water level variation speed. And we will use what's called a constant force alarm rate detector to extract the peak of the Doppler estimate from this plot, this heat map. After that, if we have multiple antennas, we can incorporate a step of doing angle of arrival estimation. All right. Such information is not necessary for estimating the propagation delay, propagation path variation, but it's important for mapping the propagation path variation to water level, right? And we also apply phase unwrapping by Kalman filter process to smooth the estimates across different time slots. So you can refer to details to this paper available on arXiv. Here I show you some experimental results. This one is for the millimeter wave system. We used a communication system for millimeter wave and extracted the CSI amplitude as shown here, right? So as you can see, in real system, the power of the CSI actually have the sinusoidal type of shape, right? And it's periodic. So it reflects, it validates what we mentioned earlier by the theoretical results. And using the technique I just described, we can achieve very accurate estimation for the water level, less than 0.02 centimeter. Right? So for millimeter wave system, we can achieve very high accuracy estimates. Now let's have a look at how its performance at low frequency. So these results show the 3.1 gigahertz result. As you can see from the figure, the dynamic range of the signal is quite large. It's quite noisy, right? And we can see like the variance is about 0.2 here, as shown here, compared to the mean power. It's something like 25%. So this directly imply, okay, the accuracy may be slightly degraded. And this is true, as we can see from the curve here showing the water level estimation results. The average error is about 0.2. It's like something like 10 times larger compared to the millimeter wave. So this is actually interesting observation. It's kind of, the accuracy is kind of proportional to the carrier frequency. Remember, we have 28 gigahertz here and 33.1 here, while the accuracy is also 10 times approximately. We further did field trials, and we placed the software-defined radio at various locations from, for example, very close to the water to 30s and to tens and even hundreds of meters away from the water, with or without a line of sight path between the SDR device and the river. So in all of the scenarios, we achieved various degree of accuracy, and the mean accuracy is about 4.8 centimeter. All right, so there's a bigger degradation, accuracy degradation compared to the controlled lab environment. Next, let's have a look at the multi-antenna scenario. So with the use of multiple antennas, we can achieve multiple potential advantages. One major advantage is with the multiple antennas, we can easily identify, for example, whether the water is increasing or decreasing simply via the power curves. All right, because multiple different antennas, different receiver antennas, they will have shifted versions of the power waveform. Right? And then at a particular time, for example, it's quite easy to identify whether the water is decreasing or increasing by jointly consider the waveform from multiple antennas. Right? So this is one of the major advantage with using multiple antennas. Another one is, of course, we can now have greater flexibility in adopting various techniques to remove the offsets due to clock asynchronism and use beamforming to achieve improved interference suppression as well as angle estimation. Right. So with the multiple antennas, we can achieve various improvements. Also, with the estimated angle of arrival, we can translate the estimated propagation path variant to the water level variation. This is because, as I mentioned, when the water level changes for a fixed connection between the user, like a mobile phone and the base station, the actual angle of arrival, it changes a little, has a very small change. I think I have a figure later. So by assuming the angle of arrival doesn't change when the water level varies, we can get a simple relationship between the actual water level variation and the propagation path variation. All right. So based on this equation, then we can translate the propagation path variation, estimated one, to the actual water level variation. So this allows us to deploy the system without any calibration. With the use of multiple antennas, we just show there are so many potential advantages. Right? So here I just show you one example how we can explore the potential of multiple antennas for water level sensing. So for example, we can construct a reference signal by using beamforming techniques with the application of reference signal construction. Then we can remove the phase offsets. We can further compress the signals by using, for example, extracting strong delayed Doppler beams over a short period, because the water level variation is relatively small, right? When there's, for example, a strong line of sight path or a high power static path between the transmitter and the receiver, the variation, the Doppler variation caused by water level can almost be ignored because the water level change is quite slow. So if we extract the strong delay Doppler beams within sub-second period, then we can remove the interference caused by fast-moving objects, for example, by moving pedestrians, by moving by the swinging trees, and by, for example, passing vehicles and boats. Right? All these movements, they will have high Doppler effects, so they can be moved by this simple technique. And we can also use beamforming to further suppress the other type of interfering signals, because we can estimate the angles for incoming paths, and based on the assumption that the reflected path is changing, but the change is slow, we can determine which path is actually from the reflection. Okay, then we can estimate the propagation delay, the propagation path length, and then translate it to water level. All right, for details, you may refer to this paper. And we tested the scheme in multiple setups, multiple scenarios. Here I show two setups. One is with the receiver close to the water. All right, it's very close, only less than 1 meter. And another one is about 35 meters away from the water. I'll probably skip the detailed approaches here. Right? It's maybe a little bit complicated, but the basic idea I have already described. And you can refer to the paper for the detailed process, in particular how we realize interference suppression, etc. I quickly show you some results. So the left one is for the delay Doppler plot or the heat map plot. Sorry, it's for the Doppler and the angle of arrival AOA plots for two paths. One is a line of sight path from the base station, and another one is a reflected path from the water. Right. So in this setup, the receiver is very close to the water. So as you can see, the reflected path is relatively strong. And this one, the right one, shows the result for setup 2, where the receiver is about 35 meters from the water. In this scenario, the reflect signal is a bit weak, but we can still see it and clearly identify its AOA and Doppler values. So based on the extracted heat map, then we can further apply the techniques as shown in the slide, in the last slide, to get the water level estimation. And the mean arrow is about 2.6 centimeter and about 3 centimeter, right? In addition to the signal processing framework, we also developed a deep learning framework. So this is one example. Basically, this is a mixed use for the fully connected convolutional deep learning network and some concatenated fully connected network, right? And we use the loss function as the mean square error between the estimated water level variation speeds and the ground truth. So this technique will require the training of the system using the collected data sets. In addition to using the dedicated or customized devices for water level sensing, we also use the existing mobile phone. And the one example here shows that using the mobile phone, we can also achieve very accurate sensing results. So the current mobile phone, it can be used to capture the received signal strength, various signal strengths, and there are multiple apps that can be used for this experiment. So once these data sets are collected, then we can use the quantized receiver signal strength for sensing. Note that the quantization step may be 1 dB also. So even with such a coarse quantized signal strength, we can still achieve quite accurate water level estimation results. Of course, in this scenario, the mobile phone is close to the water, and we tested it in both line of sight and non-line of sight scenario. So for both scenarios, the sensing performance is relatively good. Right. We also developed a real-time system and did a real-time demonstration based on the techniques I just described. In addition to using software-defined radio for sensing at the downlink, we also did sensing at the base station side. So as I mentioned earlier, the current base station devices, they cannot output CSI. They cannot even output the power strength for a single device, right? What it can offer at the moment is only the statistical distribution across all the devices in the cell. Right? So in other words, it's, for example, the probability distribution function or the histogram of the receiver signal strength or the ISRP, ISRQ, etc. Right? So such a statistical, they have a lot of dynamics. They can change with a node, a mobile phone moving into the cell and out of the cell. It can also changes when, for example, users just moving around within the cell. Right? So such a dynamics make water level sensing as well as other sensing very challenging. But we have shown that even with such large dynamic data sets, we can still achieve good sensing performance, particular for the relatively simple water level sensing. So here is one example showing that using two base stations data sets, we can estimate the water level up to accuracy about like 20 centimeters, right? Although the accuracy is not that high at the moment, there are still great opportunity for improving the accuracy. And this experiment just demonstrated the possibility. Next, let's have a look at the rainfall sensing estimation technique. For rainfall sensing, traditional weather radar already use a radio signal for rainfall intensity estimation. So this demonstrates the feasibility of using radio signals for sensing. But if we look at this plot here, we see the various this figure shows how the attenuation, signal propagation attenuation, changes with different carrier frequencies for different rainfall intensity. All right. So when the rainfall is relatively small, for example, up to the green curve, it has rain of about 5 millimeter per hour. Right. So this is a relatively small to medium rain. The attenuation for a low frequency, low carrier frequency, for example, below 10 hertz, is less than 0.1 dB per kilometer. Right? So the attenuation is relatively small. Only when the carrier frequency is relatively large, for example, at 60 gigahertz, then we can see sub dB or even larger than 1 dB attenuation. So this means rainfall sensing via radio signals seems only feasible for high frequency signals and or over a long distance propagation. All right. So this is actually true when we have a look at how weather radar works. So weather radar sends short pulses to the sky, and such a short pulses will be reflected by the rainy cloud, and the signal will actually pass through the cloud over long distance, and the typically used frequency can be quite high, all right? And then the receiver will detect the attenuation during signal propagation and use an experimental equation to determine the rainfall intensity. So shown here is the propagation distance, the water intensity, the rainfall intensity, and the experimental coefficients. Based on the measured signal power, it uses this reflectivity and rainfall relationship to determine the rainfall intensity. Right? There are, of course, various radar, and the basic one is the one measuring the power attenuation. We also have other Doppler radars, for example, other radars such as the Doppler radar, but it's mainly used to differentiate between different particles within the cloud. For example, whether there may be snow or whether it's rain, right? So it's typically the Doppler radar is not used to decide the intensity of the rainfall. So following the principle of propagation attenuation changes with rainfall intensity, people have proposed various techniques for mobile network-based solution, but most of them are limited to either high carrier frequency, such as E-band, 60 to 70 gigahertz systems, or to very long-range mobile backhaul connections. All right. In particular, the Professor Massa and his group did many pioneering work in this area. And this paper provides a good overview for the various work they have done. But in the commercial cellular network today, most of the, for example, 4G and 5G systems, they operate at sub-6 gigahertz, and the connection between mobile phones and the base station often limited to, for example, several hundred meters to a few kilometers, often not more than 2 kilometers. So within such a short period, the attenuation can be observed is quite small, right? And for conventional sensing, it's very hard to identify such a small propagation attenuation at the low carrier frequency, particularly when we consider the dynamic environment between the mobile phones and the base station, including the movement of the mobile phone itself, right? So this makes the task even more challenging. And there are also various interference similar to the water level estimation. When we started working on this project, we tried mobile phone-based sensing. So we use the similar smartphone app, capture the various power metrics, and we compared the data sets collected on the various weather conditions with without rain, slight rain, heavy rain. We try to find whether there's connections between the captured power metrics and the rainfall intensity. But unfortunately, we didn't get many interesting findings, except that we can clearly see a connection between the signal variance and the rainfall intensity. In particular, we found that the signals seem to change more rapidly during rainfall. All right, the received signal varies more rapidly during rainfall. This is the only effective observation we got over even months of dataset collection. Next, I would like to introduce some work developed by the host of my talk, Professor Jie Yang from Southeastern University. Her group did some fascinating work by using simulated rainfall or artificial rainfall. They developed a system based on software-defined radio. This is an OFDM system, and they collected the channel state information as well as the power metrics. Of course, the power metrics are derived from the channel state information, and they applied various deep learning techniques to for the rainfall intensity sensing. Before they apply the actual deep learning technique, they also characterized the various multipath performance of the received signal and try to identify the connections between these multipath profiles and the rainfall intensity. They used a 2.8 gigahertz rain attenuation channel measurement. So this is a relatively low carrier frequency. And although they can capture the CSI, their deep learning network is based on the use of the power only. Here are some of the main results from their work. So this left figure shows the instantaneous received signal strength values on the different rainfall intensities. The results seem to suggest that there's a clear boundary or difference between the results for different rainfall intensity, right? So the blue curve is for now rain, red curve for moderate rain, and the yellow one is for the heavy rain. So the ISSI seems to show quite different boundaries. This is something we didn't observe in our experiments. When they do some statistical analysis for the datasets, they show that although there are some small overlap between the PDF for different rainfall intensity, overall, they show a good boundary between the different PDF as well, right? So this is quite exciting because if we can actually see such clear differences between different rainfall intensity, their impacts on the receiver signal power, then it will make a water level, the rainfall sensing much easier. But this seems to does not these results do not seem to be have a very good match with the propagation attenuation figure we shown before. So I don't know yet what was the causes for such a difference. It could be the difference because the difference between the actual rain and the artificial rain for simulator or the simulated rain. There are also two critical observations drawn in their paper. So one is the received signal strength typically decreases with rainfall increasing. And this is common with many results shown in the work so far in various literature, various papers. But a critical question is how much difference we can actually see in the real rainfall. Another important observation is they found that the variance of the received signal strength decreases as rainfall intensity increases. They also provided some justifications for the observation, which sounds kind of convincing. In addition to characterizing the performance, the statistical performance of the received signal power metrics, they also did some analysis based on the Doppler model. Because their signals are continuously transmitted, so they do not really have the clock asynchronism issue in the system. So they just use the received signal directly and can realize the delay Doppler analysis, get the heat map as shown here. They also discussed some important observations, and their results seem to suggest that there are indeed different Doppler frequencies that can be observed from different rainfall intensity, but such a difference is not significant, and they are not very reliable if they are used as basis for the deep learning framework. So instead using the Doppler model output, they used the signal power results as we discussed earlier. And as use them as the input to the deep learning network. They use some ResNet, one for extracting the time domain feature signal, one extract the frequency domain, the spatial domain property. The spatial domain property actually corresponding to the power delay profiles, right? So it's actually the multipath feature signal extracted by using this ResNet. And then they combined them to generate the classification results. They also propose another one based on the transformer technique, and that one seems to can even achieve better performance. So this table demonstrates some of the output from the deep learning network. As shown here, the accuracy seems very high. I'm very keen to see whether keen to see that Professor Yang and his group apply such techniques to the real collected data sets and see how the performance goes. Come back to our work. We also developed some techniques based on the biostatic sensing and extracted feature signals. And such feature signals show a good consistency between with the underground benchmarking rainfall intensity measured by actual rainfall gauger. And to verify whether such feature signals is caused by other factors instead of the rainfall, we also did experiments in an indoor environment in the bathroom. All right, with a controlled experiment in the bathroom, we can exclude all the potential interference sources from the environment. And we applied a similar technique to extract the feature signal. As you can see from this figure, there are good there are some significant difference between the three types of scenarios with no water, medium rate water from the tap, or high rate. So this result validates that we can indeed apply such a technique to extract the feature signal and then further apply deep learning for rainfall intensity estimation. Unfortunately, I cannot go to the details because the techniques are still under patenting. So I cannot discuss the details for this technique, but I can show you some further experimental results. So we collected months of data and applied the techniques to extract the feature signal as shown on the bottom figure here, as well as the estimation results for the for the rainfall intensity and the actual benchmarking rainfall intensity. So you can see there's a good matching between these two. All right. Although we also have some inaccurate estimates, but roughly we can achieve relatively good estimates. The work on environmental sensing is still in its early stage, particularly for the rainfall intensity sensing. Right? Water level sensing is relatively stable, and we found it works well if we're using a dedicated and a fixed receiver. But it becomes challenging if we consider the sensing at the base station using signals from moving terminals. Right? So we say a bigger challenge is how to adapt the technique to practical environment, including moving nodes and a lot of interference sources. Another goal we want to achieve is, in addition to doing sensing for water in the river, we also try to estimate in heavy rain, in the scenario of heavy rain, whether we can estimate the water level of in the street, etc. So this is even more challenging than estimating the water level from a river. We are also trying whether using, for example, large language model can achieve improve the performance compared to use conventional deep learning techniques. Of course, this requires huge data sets. So we are still in the process of the training the network. One more challenging is about how to jointly estimate rainfall and water level, because when we estimate water level for example, flood prevention or monitoring, we try to estimate the water level when the rain is on, right? So in this scenario, we needed to develop techniques jointly estimate the rainfall and the water level. All right. So anyway, to conclude, there are still a lot of challenging problems ahead, and there are great research opportunities in this direction. So this is all for my lecture today. I'm happy to take questions if you have any. Thank you very much for your attention. This is acknowledgement for my collaborators and students, etc. Right. Thank you very much.
Okay, thank you. Thank Professor Zhang for the talk. We have received a number of questions from the audiences. So the first question is that I noticed that this architecture is applied to water level and variation height tracking. Water surfaces are typically dynamic with waves and ripples, causing severe multipath fluctuations. Is the average signal power parameters processing mentioned in the diagram sufficient to smooth out these rapid surface fluctuations and extract a stable water level reading? Or is more complex time frequency filtering required?
Yeah, thank you very much. This is a very good question. All right. Actually, we already considered such issues in our real system. And remember, I mentioned multiple interference suppression techniques for the interference that the audience just mentioned. For example, water ripples caused by wind or caused by passing boats, etc. Their Doppler, the Doppler frequency or the signal variation caused by such a movement is typically large, right, compared to the variation or the Doppler frequency caused by the water level variation, because water level changes at, for example, minutes level at least, while such dynamics caused by surrounding environment or wind or the passing boats, etc., their change is at a second level. So by exploiting such differences, we can easily apply some filter or other more advanced techniques like beamforming operating in the spatial domain. We can similarly apply beamforming like technique in the time domain or in the frequency domain to suppress such interference. Right. So the basic idea is, okay, we try to identify what's the different properties between the interference sources and the water level that we want to estimate. And then we, once the differences are identified, then we can adopt corresponding technique to separate them and then suppress the interference.
Okay, thank Professor for the very comprehensive answer. So the second question is that, is this RSRP and phase-based measurement limited by phase ambiguity within a single cycle or half wavelength? If the water level variation exceeds one cycle, causing the RSRP to wrap around, how does your algorithm determine whether it is in the first cycle or the second cycle of rising?
Yeah, that's also a very good question. Can you still see my slide?
Yeah, we can
Okay.
see.
Yeah. So as shown here, right, we for high frequency, it's easier to see multiple cycles when the water level even change a small height. The critical issue is how can we identify at which cycle we are. If we use tracking technique, we can easily track whether the water is increasing or decreasing, right? And such identification between increasing or decreasing can also be realized by using multiple receiving antennas, as I explained here, right? So once we are able to identify whether water level is increasing or decreasing, then we can safely use a tracking technique to estimate the accumulated water level variation, right? No matter whether water is decreasing or increasing. This means we will need to be able to know the initial water level. Right. So the key now becomes how can we know the initial water level when the system starts work, right? So this issue is something that we haven't found any solution yet. But most of the time we are more interested in the relative variation of the water level over the observation period. So this will already make the system very useful. Right? And to make the actual system work, we may need to, for example, output initial water level when the system starts work. Of course, we can also work out the initial water level when we have some geometrical information. For example, as shown on the figure here, I have a larger one probably somewhere. So if we refer to the figure here, if we know the, for example, transmitter or receiver height, both transmitter and receiver height, and when we estimate, get the estimate for the angle of level, we can actually work out exactly what the water level is. Right? But this requires some prior information about the transceiver height and even the distance between them. So such information may not be easy to be obtained in practice. So the simple way is probably just input the initial water level when the system starts to operate.
Okay, from this page, can we combining the power periods from the 28 gigahertz and 3 gigahertz? Could this help for the cooperation of different frequencies? Could this help resolve the ambiguity?
Definitely. That's a very good thinking. Actually, it works effectively if you have multiple bands receiver, right? So you can definitely combine the outputs from multiple receivers. Actually, multiple receivers, no matter whether they are from different channels or even working on the same channel, they provide redundant information, and such information always useful for improving the sensing performance or its capability.
Yeah. Okay. Thank you.
Not just for example different frequencies. If you have signals from multiple transmitters at different locations, etc., such information is also very useful.
Yeah. Okay.
Yeah.
Okay. The third question is, the slide notes that no clear relationship was observed between rainfall intensity and signal attenuation. Is this because rain attenuation is inherently negligible at standard LTE frequencies, such as sub 6 gigahertz?
That's something I'm interested in to know actually, because according to our experiments, it's very hard to see the difference directly associated with the attenuation due to rainfall in the cellular networks. Because if we look at this figure, that's for the rainfall sensing. So if we look at this figure, as I explained, for low carrier frequency, the attenuation for even, for example, the most heavy rain at 50 millimeter per hour, it's only, so for 10 gigahertz, it's only 1 dB. right? So if it's 3 dB, it's even lower. So this is already over 1 kilometer distance. If the mobile device and the base station is less than such distance, we may only observe less than 1 dB, or often less than even 0.1 dB power change with in the scenario without rain or with very heavy rain. So if for medium rain, it's even smaller. So in most of the experiments we conducted so far, it's very hard to only rely on the power variation of the receiver signal for rainfall sensing. But I did see in your paper you found that quite large differences observed between different rainfall intensity, and in particular as shown in the PDF here. So I also try to understand what's the cause for this. Yeah, thanks.
Yeah. Yes. In our actual measurements, we were conducted the experiments were conducted at a very close range, within 10 meters. Whereas the rain is the artificial rain, but we observe the RSS fluctuations for different rain intensity. Actually, the rain attenuation models for the you show before were conducted in a long range. It is the first difference. And the second difference is the rain. It was artificial rain, so the heavy rain is much heavier than the actually we can see in the actual scenarios.
Yeah.
And the third difference is that we not just use the ISSI for the classification. We use the CSI multipass informations in the CSI, such as the power delay profile. So in the bandwidth of our system is 100 megahertz, and we employ two receiving antennas to do this classification. So just if we just classify the rainfall by the ISSI, we cannot get the high accuracy.
The boundary and between them. Yeah. Thank you very much for the clarification, Professor Yang. I think definitely this is worthy of further investigation.
Yeah. Okay. Thank you. That's all the time we have for the question. Thanks again, Professor Zhang, for your excellent and insightful lecture on the fascinating world of ISAC applications. Thank you. See you.
Okay. Yeah, thank you very much, and thank you for your attention, all the audience. Okay, bye now.
Bye. Bye.